So in lesson 6.8, we're going to be looking at the graphs of radical functions. We're going to specifically look at square root radical functions and cube root radical functions. So the first part of our notes wants you to think about transformations of, and they happen to use a quadratic function with transformations. We actually haven't talked about quadratics yet, but earlier in the unit, we talked about the absolute value function and how the h and the k shift the function left and right and up and down. So the same thing's going to happen for a radical function as well. So what's in your notes here in this first example, they're referring to the quadratic, but just like the absolute value function from a few lessons ago, we had this. And if you remember, the h was a horizontal shift and moved the function right or left, but it kind of did opposite of what you thought because of the built-in negative. And then the k value moves a function up or down vertically, and it does exactly what you think. So the same thing's going to happen for our new function, and we're going to first talk about the square root function. So remember that if you have a radical symbol with nothing in the index, that is a square root, we're assuming, and you still have an h and a k. But instead of having a vertex like an absolute value graph would have, it's going to have a center point or a starting point. So a normal square root graph has a center point at 0, 0. And then if you think about some good points that you could plot for a square root graph, you want to think of things that are easily square rootable. So 0 is 0 when you square root it. 1 is 1 when you square root it. And then the next thing that's nice to square root is the number 4. Square root of 4 is 2. So if you'll notice 1, 2, 3, 4 up 2 is our next good point after 1, 1, and 0, 0. So if we draw a curve connecting, kind of have this side bend looking graph. It's like half of a parabola on its side. So the example they're giving you is that this particular graph has been shifted, and in the function I notice the h is a 2, remember opposite sign, and the k is a negative 3. So instead of starting at 0, 0, this guy was shifted right, 2 units right, and 3 units down. So all these points are shifted 2 units right, 3 units down, 2 units right, 3 units down. So that's one way for us to figure out some nice points and plot it without the use of a calculator. You do have to know what the original parent function looks like. That's kind of the kicker. Let's talk about the shifting that happens on each of these examples. So this one is shifted right 1 and up 2. This one is shifted right 3, but down 2. This one, remember there's a built-in negative, so inside the formula it's really like x minus a negative 4. So it's shifted left 4, down 3. And then finally here we have a left 2 and an up 1. I abbreviated my transformations with just letters. I don't mind if you guys do the same thing. So let's look at this graph again. We kind of already did this off to the side of the original example, but if we have a t-table and you get to choose whatever values you want, you are more than welcome to use your graphing calculator for these. So if you're using your graphing calculator, you go to y equals and type in your function. So I'll clear out my last problem I did. It's been a while, huh? So in y1, let's type the square root of x. And then you go to that autofill table. If your table is not autofilling, that's because you don't have it set up to autofill. So you'd have to go to table set and change the format. So you'll notice that there's a bunch of points up until I get to 0, 0 where it says error, 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 error. That's because the function is not defined. The domain is actually, it's going to begin at 0. So anything before 0 is going to be undefined for that particular function. So the first point that I notice that is nice that I want to plot is the original 0, 0. 1, 1 looks good to me. Keep going, 4, 2. And then if you want to keep scrolling down, I think there's a nice one at 9, 3. And then now that I think about that, I'm like, well, yeah, those are all the perfect squares. So if I were to put them into a square root function, 0, 0, 1, 1, 4, 2, and 9, 3. Yeah, they would come out nice. All right. And you know how my graphs go, right? So there's a really good chance this, you know what, not too bad. So this is a definite endpoint right there. Let's talk about the domain of that function. The domain is from left to right, and the domain does begin at 0. It includes 0 though, because there is an endpoint. Then the range is the lowest y value up to the highest y value. And this one's a little deceptive because I can tell the range starts at 0, but a lot of kids feel like it doesn't go up as high as they think it does. This function grows without bound. It never ever will get to a max point. So it does go off to infinity as far as it goes vertically. It doesn't look like it, but it does. All right, for the next one, if you type your function of the cube root of x this time into y equals, I should clear up my ink, see what we're doing. All right, so the cube root, this time we have to go to the math menu and pull up the cube root function, which is number 4. So the cube root of x, we don't see those errors anymore, and that's because the domain is not bounded in any way. There's no undefined values for cube rooting. You can cube root negatives, you can cube root positives, 0, everything. So you want to kind of go forwards and backwards into our chart, and you'll notice some symmetry, of course. So -8, -2 is a good point. -1, -1, 0, 0, 1, 1, and I'm guessing 8, 2. And then now that I think about those points, yeah, those should be nice because the cube roots, the perfect cubes, are 0, 1, 8, 27. Now I'm not going to be able to graph 27, so we'll leave that one alone. But let's jot down some of those points that we found. So we had -8, -2. Cube root of -8 is -2. -1, -1, 0, 0, 0, 1, 1, and 8, 2. -8, -2. And one thing I kind of forgot to do, I could have gone to my graph in the standard window and get, maybe received a picture of this. Maybe we'll do that on this one because this is an unfamiliar graph for most Algebra 2 students. So if I hit graph, that, my friends, is your cube root function. Looks like a really stretched out like S. That's exactly what it should look like. There is kind of a center wiggle point, if you will. In this case, it's at the origin. That is one of the points that you would see easily translated. So if I knew it was shifted right, left, up, down, that's one of the points that I would move myself. Domain is -infinity to infinity. There are no restrictions. The range, again, this is a little deceptive because a lot of kids think it kind of flattens out, especially if you draw like me and you did a bad job. It does go down and up forever. So the range is also -infinity to infinity. It just grows really, really, really slowly. So, sorry. All right, so let's see here. Graph something times the square root of x, and then we're going to keep changing that something. So 2, 1/2, -3, -1. And then we're supposed to write down some comments, right? So back to your function, y equals menu. I already forgot what they were. Let's do 2 and 1/2 at the same time. All right, so I'll do the mother function, the original function in y1, and then 2 times the square root of x right here. And then we'll do 1/2 times the square root of x in y3. All right, so blue, red, okay. There's the original, there's the 2, and there's the 1/2. So notice the center point, if you want to call it that, the starting point is still at 0, 0 for all 3 of those functions, but the 2 times square root of x was the red one. That one was vertically stretched and started to go higher, grew at a faster rate. The 1/2 was lower to grow. So I think that kind of makes sense as far as our knowledge of what a vertical stretch does to everything. Now the other thing they wanted us to do, lost my paper, was try -3 and -1. Well, I mean, spoiler alert, what happens when you throw negatives in front of a function? I'll tell you. All right, so here, if I insert a negative and then change that 2 to a 3, I'm just going to graph. Oh, man, I did 32. Dumb. Get rid of the 2. Well, I saw what -32 did, and it was not good. All right, -3. So it would be the red one I'm looking at. So, yeah, it reflected it over the x-axis, which I anticipated because of the negative in front. And then it grew faster, if you want to call it that way. It's going much steeper. It's increasing the y value, or in this case, decreasing the y value much, much faster than normal. So the question is, Especially notice how the label points of graph, blah, 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 change. Okay, so the y values, when you have an a value that is, let's consider it larger than 1 if you take the absolute value. So the absolute value of a, it's going to be a vertical stretch. So 2 and 3 are vertically stretching. If a is negative, then buzzword, it's reflected, oh man, over the x-axis, like all functions are. And then if the absolute value of a is less than 1, so that's when you had like the 1/2 right there, that is called a vertical shrink or compression. And essentially it just means the y values are increasing half as fast as they used to increase on the original function. So how does a blah, blah, blah? We already talked about that. Okay. So this one, it's up to you how much calculator you want to use on these. We're typing a square root function this time, and it's been shifted. So this +1, -3 are the shifts. So it's been shifted left 1 unit and down 3 units. So if I was just kind of matching them up to a bunch of graphs that were offered, I should be able to tell pretty quickly that it was a square root graph that's been shifted left 1 and down 3. So instead of starting at 0, 0, I know it's going to start at -1, -3. Now from there, I might have a tough time coming up with points on my own. So at this point, it would be fine for you to go to your table, type your function into y1, and get some good points. Good job, bud. All right, so I already knew -1, -3 was a good point. So go ahead and pause the video, get this typed into your y equals menu, and look at your table for the next few good points. So I'm going to do this without my table. This should be a challenge, right? All right, so -1, 0, 0. If I plugged in a 0, that'd be square root of 1, so -2. And then, let's see, 3 would be a good point because 3 plus 1 is 4. Square root of 4 is 2 minus 3 is -1. That's good enough for me. All right, 0, -2, and 3, -1. Oh, now it helps if you can actually draw, which clearly I can't. All right, so that's why we made erasers. The domain of this function begins at -1, goes to infinity, and the range for this function begins at -3 and goes to infinity. So I know everyone's always trying to make connections and shortcuts, and they're saying, oh, wait. So the h value is the beginning of my domain, and the k value is the beginning of my range. And I'm going to say generally yes, unless it has some weird reflection going on. We do have to watch out for that. So for the ones I give you, they're going to be pretty simple. All right, and that's specifically for a square root graph. The next one is similar, but it's going to be a cube root graph. So this cube root graph, remember, it usually wiggles at 0 in that middle wiggle point. It's been shifted right 2 and up 1. It also has a vertical stretch of 3, and because there's a negative in front, it's been reflected over x-axis. There's a lot of stuff going on. If I asked you to identify all the transformations, I would expect you to identify all of those. Shifting right 2, up 1, a vertical stretch of 3, and reflection over the x-axis. All right. So if I want some good points, you're going to have to get this typed into y1. And I could probably do this without my table on my calculator. Let's see. Go ahead and pause the video if you want it typed in for your calculator. Otherwise, hang with me. We're going to get some good points. Ready? Let's see. A nice thing to cube root would be, oh, it's not cube root. Square root. Duh. Okay, either way, all these transformations are the same. So its square root would have been like this. But all those shifts are going to be the same thing. So the first thing that's nice to square root is 0. So if I put a 2 here for x, that would be 0, square root of 0 is 0, and your 3 times 0 is 0, plus 1 is 1. I already need that now. Okay, the next thing that's nice to square root would be a 1. So putting a 3 right here would work. 3 minus 2 is 1, square root of 1 is 1, -3 times 1 is -3, plus 1 is -2. So you're seeing how this is going to be reflected and it's going to kind of grow or not grow really fast. And then the next nice thing to square root is a 4. So if I put a 6 right there, that's square root of 4, which is 2. Negative 3 times 2 is negative 6, plus 1 is negative 5. All right, so again, a little bit of artistic ability helps. Oh gosh, that was not supposed to look like that. Something like that as a definite starting point right there. So remember, this has a reflection, so that old H and K formula that a lot of kids are trying to use won't work. The domain is still 2 to infinity. So that rule does work, but the range, we got to be careful. It actually goes down forever, so negative infinity and then stops up here at 1. So I've said this before, but I don't really like to use formulas. I'd really much prefer just to look at the graph in order to come up with what's going on. All right, so now we have cube root graphs. These are the ones where they go forever. This one has been shifted left 2 and down 1. Also has a vertical stretch of 3. So it's going to be going up and down a lot faster than the original one. Actually, some kids think it's easier to graph that way. All right, so if you want to pause the video right now to get some good points, that'd be fine. The negative 8 is a good number to cube root. So in order for this to come out to negative 8, that would have to be a negative 10 in the x. So negative 8 cube rooted is negative 2 times 3. Negative 6 minus 1 is negative 7, I think. Yeah. And then negative 1 is a good thing to cube root. So in order for this to be a negative 1, x would have to be a negative 3. Cube root of negative 1 is negative 1. Times 3 is negative 3. Minus 1 is negative 4. You could just pull these off the table, guys. 0. So if this was a negative 2, that'd be good. 3 times 0 is 0. Minus 1. 1. This would have to be a... I did something wrong. No, I'm good. Negative 1. Negative 1. Okay, so cube root of 1 is 1. 3 times 1, 2. And then for that to be an 8, x would have to be 6. 3 times 2 is 6, minus 1 is 5. All right, so those should match up to the table points as long as you typed in the function properly and as long as I actually came up with the right points. So negative 10, negative 7, negative 3, negative 4, negative 2, negative 1, negative 1, 2, and then 6, 5. So there should be some symmetry, and I do see it, so I must have done something right. And it is definitely vertically stretched, and I can tell that that little center wiggle point has been shifted left 2 and down 1, so I think life is good. So domain goes from negative infinity to infinity. I gotta yell at my kid again, hold on. And the range is also negative infinity to infinity. Don't know if I ever came up with that on our original notes back here. Yeah, I did. Okay. So a good question is that always going to be the domain and range? And the answer is yes. For a cube root, it is. All right, this next one, these are not going to be very good points. I'm just going to warn you. So I'm going to go ahead and get this on the calculator so I don't have to think real hard. I know, from a teacher, that's awful. But I'm tired, and it's the summer. Okay. So 2/3. And then it was cube root, right? I've done this before where I make it up. All right. Cube root. Menu. 4. Root of x. All right. So if you want a sneak peek of it, you will see what looks like a normal cube root graph, but it actually is a little bit vertically compressed. But we're going to want to pull some points off the table. And I'm telling you, they're not going to be pretty, guys. So 0, 0, woohoo. That's really slim pickings as far as good points. You'd have to go pretty far out to get a really good point. In fact, so far out that we're going to have to fall off of our graph. So I'm just going to kind of fudge it in here if you don't mind. Whoop. Oh, gosh. Yes, dear. Oh, I'm still hungry. The internet's going to think I don't feed you, baby. Pretend I grab it. I'm going to get my kids some food. I'll be right back. Why what? Get your food. All right, we're back to a square root graph. So you can come up with points off your table and your calculator. I'm going to try to muscle through this without using the calculator. So the first thing, so the first number that's nice to square root would be a 0. So putting a -1 in for x would do that. So 0 times plus 3 is 3. The next nice thing to square root is a 1. So putting a 0 here would work. So 2 times 1 plus 3 is 5. And then the next nice thing to square root is a 4. So if I put a 3 here, that'd be square root of 4, which is 2. 2 times 2 is 4, plus 3 is 7. And that's good enough for now, guys. So -1, 3, 0, 5, and 3, 7. So I didn't talk about the transformations before we came up with these points, but I should have said that this was shifted left 1, up 3, and it has a vertical stretch of 2, which is exactly what I see. Left 1, up 3, vertical stretch. I mean, it's hard to tell what kind of vertical stretch you have, but I can see there is one. So the domain begins at -1 and goes to infinity, and the range begins at 3 and goes to infinity as well. All right, careful, we're switching to a cube root graph again. I think this is our last example, so good news. All right, so cube root. Again, if you want good points off your table, go get them. If you don't have a calculator, that's okay. We can still do this. So the lowest nice thing to cube root, in my opinion, is -8. So I think about what would I put right here to make this -8, and that would be -9. So -8 cube rooted is -2. 2 times -2 plus 3 is -4 plus 3, so -1. The next nice thing to cube root is -1. So in order to make this -1, x would have to be -2. So cube root of -1 is -1. 2 times -1 is -2, plus 3 is 1. 0 would be nice. So if I want this whole expression to be 0, I'd put a -1 here. While I'm at it, plugging in a 0 would give me 1, which is another good thing to cube root. And then 8 is the next nice thing to cube root. So if x is a 7, all right, really on a roll there. All right, let's plug all these in. -1. So cube root of sorry. Ding, I switched colors. They can't hear it though. Here, watch the video. All right, so -1 plus 1 is 0. Cube root of 0 is 0. 2 times 0 plus 3 is 3. Okay, cube root of 1 is 1. 2 times 1 plus 3 is 5. And then cube root of 8 is 2. 2 times 2 is 4 plus 3 is 7. All right, that should be enough points, right? Right, Logue? Not sure about that. All right, -2, 1. -1, 3. 0, 5. 7, 7. All right, so again, I'm looking for symmetry. I'm looking for it to confirm the transformations that I once again forgot to say at the beginning. Oh man, that was almost dynamo. All right, so I should have said at the beginning that this was shifted left 1, up 3, and has a vertical stretch of 2. So left 1, up 3, vertical stretch of 2. Sounds appropriate. All right, the domain and range are always -infinity to infinity on cube roots. What do you think about that, Logue? I know, it's nice to look at, all right? Good luck. Lots of graphic calculator usage ahead of you.